Okay, first of all, I will need to do something that I absolutely unexpectedly failed to do last time, and this is a very embarrassing moment because actually the proof is one line as I anticipated, but I could not find that one line last time. And I will need this, so let me start with this. So let A be compact convex subsets of Rn, compact convex. And as we know, A plus B is a notation for the set of sums A in A, B in B. It is quite easy to see that this set is compact, convex. So this is a well-defined operation. We will need the following lemma, small lemma, very easy, which I formulated last time. Extreme points of A plus B are a part of extreme points of A plus extreme points of B. And even more so, if, say, C belongs to vector A plus B, then there exists unique A belonging, better to say, A in A, B in B. Exclamation mark means unique, such that C is A plus B, and A belongs to extreme points of A, B belongs to extreme points of B. So actually this representation is very non-unique generically. For each point in A plus B, there may be a lot of representations as the sum of two vectors, one from A and the other from B. But for a specific vector, that means for extreme vector of the sum, this representation is unique, and A and B are nothing else but extreme vectors. One thing more, these do not need to be the same. The sum of extreme vectors may be not an extreme vector. And an example is very simple. This is a convex set. This is another convex set. Oh, I could have done much better. They do not need to intersect. Let me do it this way. Convex, convex, in one dimension. What is the set of sums? The set of sums comes if you add this and this vector, you will get one vector. If you add this and this vector, you will get another vector. And everything between. You can easily see that everything between. Is everything between? Okay, if they're close enough, then everything between. But for example, if you add these two vectors, these two, this and this, it is not going to be an extreme vector. Obvious reason. Okay, so I will need to prove this lemma, and the proof is really one line.
The exclamation point means
Unique.
unique.
Or in other words, exists very much. A proof is very simple. C belongs to extreme A plus B. Therefore, C belongs at least to A plus B. then there exists A in A, bad, B in B, such that C is A plus B, just by definition of the sum. Assume the opposite. At least one of them is not an extreme point. Say A is not extreme point. What does it mean? Something is not an extreme point. Then this vector is an interior point of a segment with ends in the set. Correct? Then it does not belong. Then there exist A1, A2, both not equal to A, such that A is lambda A1 plus 1 minus lambda A2, lambda between 0 and 1. This is exactly a description of an interior point of a segment. Okay? Then consider A1 plus lambda B1. And consider, A1 plus B1, it belongs to A plus B, plus B, and A2 plus B belong to A plus B. Consider these two vectors. A1 plus B belongs, A2 plus B belongs. Consider these two vectors. Then A plus B, which is C, is A is lambda A1 plus 1 minus lambda bit A2, plus B I will write lambda B plus 1 minus lambda B. Believe me? A is written as it should have been written. B is written in an obvious way. Okay? Which gives me lambda A1 plus B plus 1 minus lambda A2 plus B. This belongs to A plus B. This belongs to A plus B. Correct? I have a convex combination of these two. And the only thing I have to check is that A1 plus B is not A, and A2 plus B is not A either. Easy. Is it easy or not? It's not C. I am C. It is not C, and this is not C. Which is easy? C is A plus B. So B's cancel out, and A1 and A2 are not A's. End of story. As you see, this is indeed one line, a long but one. Okay, but there is something that we will need, and I want to repeat it. If you have a vector from the sum, it can be represented in this form in many ways, generically. But there are especially important vectors, which are extreme vectors of the sum, which can be represented in this way uniquely. And this representation involves two extreme vectors. Okay, I've proven everything, and let me move forward. I'm sorry.
Prove the uniqueness.
Uniqueness, yes. Did I prove the uniqueness? Okay, I did not prove the uniqueness, but I will do it in a moment. Uniqueness. Actually, it follows. Assume the opposite. C is A plus B, and it is A tilde plus B tilde. Then C is 1/2 C plus 1/2 C, which is pretty obvious, which is 1/2. For this C, I will use A plus B. For this C, I will use A tilde plus B tilde. And this is 1/2 A plus 1/2 A tilde plus 1/2 B plus 1/2 B tilde. And this is not, therefore, it is, I call this A 2 tildes plus B 2 tildes. So C has a representation A 2 tildes plus B 2 tildes, and A 2 tildes and B 2 tildes are obviously not extreme, which is not possible by the previous consideration. So A 2 tilde, B 2 tilde are not extreme. It's enough, only one of them. Which is impossible by the previous. Okay, so I think, yes?
The extreme points aren't precisely the same as the boundary, right?
No. Okay. For example, if you have a square, extreme points are only the vertices, but points on the straight part of the boundary are not extreme. Extreme points are, say, extreme. You cannot get them from anything else. And I want just to repeat the definition of the mixed volume, because I will need it right now and I want to repeat it. Let A1, A2, AN be convex compact sets of Rn. N and N are the same. Okay. The mixed volume is the following. Let me do it for small, for n equal 2, for example, then we will see that actually nothing is needed. But I will show how to extend it to 3. Is volume of A1 plus A2 minus volume A1 minus volume A2 divided by 2. The volume on the right hand side is the usual volume. A1 plus A2 is a convex compact subset of R2. So its volume is area, is it? And V of A1, its volume is also area. V of A2 is also area. And this is a very nice formula. Where do I get it from?
The sets are disjoint.
Not necessarily any two sets.
But if the sets are disjoint, you get 0.
If the sets are disjoint, I'm not sure why.
A1 and A2.
No, A1 plus A2 is the not simply the union of them.
Oh, something else.
It is the set of sums. I know. Set of sums. It is better just to try. Let us do something very simple. For example, I can take two convex sets, a square and a circle. What is the area of the square? We know. What is the area of the circle? That we know. So what is this sum? This sum is a convex set. How do we get it? It is a convex set. In order to have a convex set, we only need its extreme points. If we know extreme points, then we know the whole set. How do we get extreme points? We have to add extreme points of one to extreme points of the other. So there are 4 extreme points of the square, are they? To each of these points I must add all extreme points of the circle. How many are there? All boundary points of the circle are extreme. So if I add, if I take all points of the circle and I add this, what do I get? I get a circle simply moved here. I get a circle centered here. Do I? If I take all the points of the circle and add them to this vector, I will get a circle moved. Just a moment, I have to understand. This is, so this is the origin. I will get a circle moved here. Believe me that this is a circle. Okay? Then I get the third circle. And the fourth circle. So all extreme points are here. Now I must take the convex hull. What I get is this convex body. Correct? What is the area is very well understood. Area minus area minus area, and we are done. Another example, maybe a better example. Consider 2 polygons.
I'm sorry, back to this example. A plus B means the convex hull of
No, it means the set of all sums.
the set of all sums.
Might be easier
Sums.
with
Okay,
two
right,
squares.
right. Yeah, okay.
The set of all sums, but we've got just erased this lemma, which describes the set of extreme points of the sum. Extreme points of the sum are obtained by summing extreme points of one and of the other. But if I know extreme points, I know the whole set, because I simply must take the convex hull of extreme points.
Okay.
2 squares might be easier, right?
Huh?
Take 2 squares.
2 squares, yeah, sure it is going to be easier.
Square is twice the size of the original one.
Okay, let me do 2 squares of this sort.
Put them in the same orientation. You just
Yeah, I understand, but it is going to be too easy. Let me do it this way. So I have a square and 2 squares rotated with respect to each other. So what must I do? I first find the extreme points. What are the extreme points? To this, I must add these 4. What I get Come on, half. These are the extreme points of here. These are extreme points when I add all these 4 points to these. You get it? Then these are extreme points here, and these are extreme points here. As you see, these extreme points are actually not extreme points. But what I get this wonderful figure, which is the sum of these two squares. Which is the sum of these two squares.
So the mixed volume is just the area enclosed by the convex hull
Minus area of 1 minus area of 2. It is for 2 only, divided by 2.
Okay, so that first term is the okay.
So I must take the area of this guy minus area of this minus area of this, divide by 2, and I'm done.
Where's the 2 come from?
What's the purpose of the 2?
2, okay, that's a good question, and I will answer it. A very good question. 2, where does it come from? I will just remind you what this means. What is this in general? And then the origin of 2 will become obvious. It is the following. This is obviously a function of n convex bodies in the n-dimensional space. I want it to be n linearity with respect to the addition. Okay. I want it to be symmetric. That means if I switch 2 of them, the result is not going to change. Then there is a general result from linear algebra, which says that n-linear symmetric form of n variables is fully determined by its restriction to the diagonal. So if I know only this, guys, for all a's, not a's, only this, for all a's at all, then I can reconstruct this with the help of the, for example, with the help in, if n is 2, with the help of this formula. But this formula, which is called the polarization formula, exists for any n. Let me try to do it for to do this formula for n equal 3. I do not remember them by heart, but I will do this, I hope, right now.
Is it obvious this is linear? V is bilinear?
No, the thing which is...
V2 of A1, A2, is that?
Well, if it is described by this, then it has to be
Now
linear.
that you've told us about the sum, it's not so obvious that V of A1 plus A2
It's a good question.
will
Let me. Actually, it is better to put it in the other way around. It is better to put it the other way around. If you know all these for all a's, then you can construct this and prove that this is going to be indeed an linear symmetric function. Let me show you how this can be done. This is a simple thing which actually is it is simple algebra. First of all, AB plus BA is A plus B squared plus minus A squared minus B squared over 2. It is true for any multiplication which is bilinear and symmetric. Symmetric means commutative. Because how do I open these brackets? A squared plus B squared plus 2AB, correct? A squared and B squared get cancelled out. 2AB over 2, I get AB. Or if since AB and BA are the same, I get what I need. Okay? It is actually, then it is without 2. I'm sorry. Let me do it for 3. I need to know ABC. How can I get it? First, I need to take A plus B plus C and cube it. Because one of the terms will be ABC. When I open this, one of the terms is going to be ABC. And I must take care of all other terms. What are the other terms? A plus B plus C cubed is A cubed plus B cubed plus C cubed plus 3A squared B plus 3A squared C plus 3B squared C plus 3BC squared plus I think 6ABC. 6ABC or not? Just a moment.
You don't need 3b squared c twice. You just
Say it again. Let me see. It is easy. A plus B plus C. A plus B plus C.
oh, then we need ab squared.
AB squared, yes.
And ac squared.
And AC squared. I missed something. A plus B plus C. If I multiply out, A cubed, B cubed. Now, 2 A's and B. How many times it will happen? These 2 A's B, these 2 A's B, and these 2 A's B. 3 times it will happen. Correct? And so on. I think this is a correct formula. I have a very strong feeling that this is indeed a correct formula. So what do I get? So I am interested only in this guy, ABC. I know that I will have to divide by 6. I already have this, and I have to subtract. I certainly need to subtract A cubed, B cubed, C cubed. Correct? Now, what else do I need to subtract? This is left. These guys are left. Let me see how can I fight them. Not such a big deal, but I need a bit of careful thinking. If I take these two, it will be 3AB, A plus B. I think I need to take A plus B. I think I need to add. Just a moment, give me a moment. A plus B cubed, I add it. And I need to do something to subtract something that I don't want. What am I going to subtract? A cubed and B cubed will be here, and I do not need them. So I put 2 here and 2 here. What else will I have here? I will have 3A squared B plus 3AB squared. Correct? 3A squared B plus 3AB squared. And it is exactly what I want to get rid of. So I need this. But I also need a plus c cubed. What do I pay for that? I will kill these two guys, correct? But I need to take one a cubed, so 3 here, and one c cubed here, correct?
I'm looking at the signs. You want minus a plus b cubed. You want to kill terms. You don't want to.
Oh. Yes, you are right. I want minus here.
That's going to make these cube terms simpler also. Good.
And this indeed will make minus a cubed. So actually I will have only c squared here. C cubed, I'm sorry. Because a squared plus b squared will disappear. If I only take this. If I only take this one. Because here I will have to add a cubed plus b cubed, and a cubed plus b cubed has been already subtracted, so they cancel out. Okay, let me do it better. Let me do it better. It is.
Write down the answer. No. Don will write down the answer for you.
Come on. ABC is a plus b plus c cubed minus a plus b cubed minus a plus c cubed minus b plus c cubed, and I think plus, yes, right, plus a cubed plus b cubed plus c cubed. For sure, this is the right answer, and should be divided by 3 factorial.
B plus C cubed.
Say it again.
B plus C cubed.
A plus c cubed
The next one.
With the approximation that 3 is equal to 2.
cubed, yes. You know,
B plus C squared.
okay. You understand that 2 means 3 if we need that. They're not that much different. Let us simply check this formula. Now I understand the formula. A cubed will be here, a cubed will be here, a cubed will be here. How many? A cubed minus a cubed, 0, minus a cubed plus a cubed, 0 all in all. Now, what else is going to be here? The same with b's and c's. So here I will have 3a squared b, a squared b. And here I also have minus 3a squared b. Cancel out. What else do I have? And the only thing that survives here is 6abc. Divide by 6 and you get abc. Actually, you can easily, I think that I can easily do it for 4. Could someone help me with that? I take the sum of 4 minus the sums of 3's, a plus b plus c, a plus b plus d, b plus c plus d, what? A, B, C, A, B, D, and, oh, I need something. A plus C plus D. All possible combinations of 3 minus B plus C plus D. 4 choose 3. Exactly what it should be. So 2, as you understand, is definitely 4. Now plus, I must take all pairs. Okay, and minus, I must take all singletons and divide by 4 factorial. Homework assignment. Prove it for any n. Find the polarization formula for any n. You see, in order to memorize it, you need to do something really hard, but you can easily reconstruct it. Okay. Now, you can use it the other way around. You can, if you know all these expressions, then you may simply define ABC this way. Actually, the only thing that we were using here is the following. We have used linearity with respect to each of the arguments. We have used symmetricity, and that's it. Nothing else. We have used symmetricity and nothing else. So that means that if we have symmetric and nlinear expression, then we can reconstruct this expression if we know it only on the diagonal. Diagonal means all the arguments are the same. And from this formula, because we are reconstructing by this formula, from this formula it easily follows that it is going to be nlinear and symmetric. It is a small algebraic proof, but you can do this. We are reconstructing by this formula, and a simple, straightforward proof will show you that you indeed get a linear form. Yes?
To match that formula, should it be, for the 2k, shouldn't it be something like b of a1 plus a2, comma, a1 plus a2?
Say, this.
Shouldn't all of those b's be have two arguments?
Yes, but that really means a plus 2, comma a plus 2.
Yeah.
This means a1, comma a1. This means a2, comma a2. Mm-hmm. 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 Yes. So the thing is now the definition which was already presented last time. This expression.
How are we doing though? This formula is excellent, yes, but how does it connect up to the original formula? You have a volume.
Okay, yeah, I'm just explaining right this.
I can see if you have squares, I can see.
Okay.
Have little squares, nothing but squares.
Okay.
I can see how it's going.
So by definition, this expression is a symmetric and linear expression in all of their arguments, such that if it is being, let me put n here, restricted to the diagonal, it gives simply the n-dimensional volume of A. It is the definition. You definitely have to check that the n-dimensional volume has the necessary properties, that after you do this you will get an n-linear form, because n-linear, you get an linear form. But it is, again, this is a good question to address. Prove that the usual volume does have the necessary properties. By the way, it's not easy. It was the main result of Minkowski.
Well, we should just be able to dash it off.
If Minkowski could do it many years ago, why can't we do it right now? So definition is this. I think it is not very usual for, say, a physicist or anyone outside of mathematics to agree to such a definition, but this is the definition. So again, this is an n-linear form, symmetric n-linear form in n arguments, whose restriction to the diagonal is the usual volume. And now I can answer your question about why, say, 2 is important and so on. In this formula, try to replace this by this. It should be, since it is going to be linear, lambdas should go out, correct? So it should be lambda to the power n, Vn of A. which is, if everything is okay, is simply the volume of A. But this must be true. If I inflate A by lambda, the volume must increase by lambda to the power n. The volume does have this property. If the volume did not have this property, then our definition would have been self-contradictory. I understand actually now I can address your question much more precisely than I did before. If you have a quadratic form, x squared minus xy plus y squared, it is a quadratic form in xy. Correct? This is simply a function of a vector xy. But it is not any function. It must have some properties. Correct? In order for this function to be a quadratic form, it must have some properties. What properties should it have? The properties it should have are can be formulated exactly the same this way. If I apply this function, if I plug this function into a polarization formula, what I get is going to be symmetric and linear in each of the arguments. This is exactly the condition for this form to be a quadratic form. The difference between quadratic form and bilinear form. What is a quadratic form? You take bilinear form and restrict it to the diagonal. Correct? And the question is, which functions can you get this way? How to describe quadratic forms? So if you have a bilinear form and restrict it to the diagonal, you get what is called quadratic form. Question: what functions are quadratic forms? Answer: take a quadratic form, use, for example, this formula, polarization formula. You will get some function of more variables. Require that this function is linear in each of the arguments and it is symmetric. This is exactly the conditions the quadratic form should satisfy. Now I think I have answered your question. Have I?
Well, one of them. The question still remains, is that function V2 linear in A2?
That is exactly, okay, this is a theorem.
Mm-hmm.
This volume, this function, A goes to volume, usual volume of A, is not quadratic but n form, is a restriction of a uniquely defined n linear form to the diagonal. It is a theorem. Let me just formulate it as a theorem. And I believe it is due to Minkowski. A restriction of a unique n linear symmetric form to the diagonal. It is a theorem, and again it is non-trivial. Not awfully hard, but non-trivial.
Now, this theorem that you wrote, the V2 expression,
Mm-hmm.
you've given us the information so that if I have two squares
Mm-hmm.
in the same orientation, they don't have to be the same size, two squares in the same orientation, I can do that calculation mentally in my head and see that it's the right formula.
Yes.
How do I do it for two arbitrary shapes?
Minkowski did it for you.
Uh-huh.
Minkowski did it for you. Again, this is not a trivial fact. Not awfully difficult, but definitely non-trivial. Minkowski was a pretty good mathematician. If his name is attached to this result, then it is not a trivial result. But it is I think this is a very important mathematical notion that should be much widely known than it is, and it definitely, and now we already understand that it has a lot of very useful applications. So we better know what it is. And the question, Jens, your question was, why I cannot have two bodies in 25-dimensional space and use this formula and get a mixed volume. No, I will not be able to do this because of this consideration. I think it was your question. At least the thing is, again.
That was more intelligent than the question.
It was actually a question that I asked myself when I first heard about this. Why do I need to have the same number of convex bodies as the dimension of the space? And the answer is, if I want it to be the n-dimensional volume, then it must satisfy the homogeneity condition, the right homogeneity condition. And this homogeneity condition arises only if you want it, if you have n bodies in n-dimensional space. Because otherwise you can put it here, but you will not get an n-linear form. When you do this polarization formula, you will get some function, but who guarantees to you that it is going to be linear in every argument?
The answer to the question why the 2 is simply that if A1 equals A2, then B2 should be the volume of A.
Okay, I think it is quite easy. If A1 is equal to A2, then this is simply twice the area. So twice the area, that means it is 4 times the initial area. Twice the size, linear size. That means 4 times the initial area. Minus this, it will be 2 times the initial area. Divided by 2, you are okay. We got it.
You have 2 amoebas that are identical, and you add them together. 2 sets whose boundaries are shaped like an amoeba. Do you have a set of the same shape?
No. This. No. If I add 2 shapes, I will get this of the same shape, but twice the linear. It will be dilated by 2.
Be exactly the same shape.
Yes, sure. Simply because there is a simple formula. A plus A is 2A, which seems to be a trivial formula, but it is not. A plus A you add as Minkowski taught us to. 2A you dilate it by 2. And the result is you get the same. So you try to explain to a kindergarten, or not, say, elementary school kids that this is a deep result. A plus A equals to A. What?
You did that by considering the extreme points?
For example, extreme points is a very good way. You can do it straightforward, but extreme points is a good way to do it. So this is a very important result. A plus A is indeed 2A. Did I explain what I wanted to? Very good. Okay, now at last we have. I'm promising in I think the 4th time to explain a relation to systems of equations, and it is high time to do this. And I have several minutes to do it. Now. Okay, let P be a polynomial in n variables. n variables. Fix a system of coordinates. Fix coordinates. It is a coordinates. The notion is attached to a system of coordinates. Then P of x1 xn is the sum a alpha x alpha. X alpha by definition is x1 alpha 1 xn alpha n. Alpha is a multi-index of integer with integer coordinates. This is a definition of a polynomial. Okay. Support of P is, and again I have fixed the system of coordinates. The support also definitely depends upon the choice of the system of coordinates. Is the set of alpha in Z such that A alpha is not 0. Support are all coefficients, all non-zero coefficients appearing in this polynomial. So actually I can write here that alpha belongs to support of P. By definition, this is a part of Z plus n, which in turn is a part of Rn. Z plus n is a part of the lattice, integer lattice in the n-dimensional space.
Strikes me to ask, what is Z plus? Does Z plus include 0 or only 0?
Yes, it includes 0.
It includes 0.
Yes, it includes 0. Actually, we are interested, what we are doing, what we are talking about is actually good not only for polynomials, but for Laurent polynomials. When I allow alphas to be not necessarily positive, but also negative integers, nothing changes. The so-called Laurent polynomials. Then definitely this is going to be in Zn, not plus, but nevertheless it is in Rn. And this is a finite set. By definition of polynomials, this is a finite set. The Newton polyhedron of the polynomial is Newton of P is the convex hull of the support of P. I have finitely many points in the n-dimensional space. I am very tempted to consider the convex hull of these points. And this is called the Newton polyhedron. There is an understanding that all, say, stable characteristics of polynomial are hidden in its Newton polyhedron. All calculable, stable characteristics of a polynomial are hidden in its Newton polyhedron. So looking at the geometry of this polyhedron, you can compute a lot of natural, stable characteristics. Now, S of, let this call it also A. It is in convex Rn. It is a convex compact set in Rn. S of A is the set of all polynomials such that Newton polyhedron is a given convex set. So for each convex set, I consider all polynomials whose Newton polyhedron is exactly this set. Definitely there are very many such polynomials, but what is the difference between all these polynomials? Coefficients. First of all, their possible powers are in the given subset, correct? But I know nothing about their coefficients. The only thing I know that the coefficients sitting in the extreme points, coefficients related to the extreme points, must be non-zero, because otherwise these points will be in the Newton polyhedron. But otherwise I know nothing. For any alpha in extreme of A, and for any polynomial in S of A, P alpha, okay, I will put it this way. The coefficient at alpha is related to the alpha derivative of the polynomial, correct? So that's what I know. For any extreme point, the related derivative of the polynomial from this set must be non-zero. But I know nothing about the precise values of these coefficients. I know nothing about the precise value. Now I want to understand what is a generic polynomial with a given Newton polyhedron. Not a generic, what set of polynomials with a given Newton polyhedron I will call a generic set. I better say which sets I will call non-generic. Everything else, all other sets are generic. A set of polynomials with a given Newton polyhedron is called non-generic if the coefficients of this polynomial satisfy an algebraic equation. If the coefficients satisfy a non-trivial algebraic equation. It's simply algebraic equation. I don't need the word non-trivial, any. I want to. Okay.
I think you're going to have to explain that.
Yes, that's what I'm going to do. Let me do it in two-dimensional case. Let this be a polygon, convex polygon, with integer vertices. Why do I need integer vertices? Because otherwise it cannot be anyone's Newton polygon. Okay? So that's. Consider any polynomial whose Newton polygon is this. Any polynomial. What do I know about this polynomial? I know that the coefficients sitting here must be non-zero. And I know that all non-zero coefficients are what is inside. There are no non-zero coefficients outside. So I have some freedom in choosing the coefficients. What is the freedom? The number of integer points in the polygon. It is exactly my freedom. Correct? the number of integer points in the polygon. So I have a freedom of choosing a finite number of complex numbers. Okay. A set of polynomials is called non-generic if the related set, so if the related numbers, what are numbers? Numbers are coefficients of this polynomial, do not satisfy an algebraic equation. A set is called if they do not satisfy an algebraic equation. So better to put it maybe this way. Consider an algebraic equation of how many variables? The number of variables is the number of integer points in the polygon, correct? Consider any algebraic equation on these unknowns. Consider all unknowns which satisfy this equation. There are very few of them, as a matter of fact. In the huge dimensional space, it will be only a hypersurface, correct? If I have one equation, then all points satisfying, they form a hypersurface. Hypersurface is a very small part of the space. So all polynomials whose coefficients are on this hypersurface form a non-generic set.
Okay, I'm not quite getting it. If one of the coefficients is 1 and the other coefficient is 2, then 2 times this one minus that
Yes.
one equals 0. That's an algebraic
Every
equation.
one polynomial definitely is a very specific polynomial. It is non-generic. What I'm talking about, not one polynomial, but about sets of polynomial. You're right. Every one polynomial is very generic.
It's very non.
No, it is very non-generic. It is very special. It has its, say, social security number and so on. Yes? But I'm talking not about one polynomial. I'm talking about huge sets of polynomials. So that means non-genericity, being non-generic means that I am very free to change the coefficients. Coefficients are not bound to any algebraic subset. I'm very free to change them.
Your freedom comes in the size of the
Yes, exactly. The size, it comes in the number of integer points inside the Newton, say, polyhedron.
So is this algebraic equation going to come from the Minkowski mixed volume then?
No. It's quite a different thing. It's quite a different thing. So now I can go one step further. Should we? Let me go this step further the next time, if you don't mind. Actually, what I have told so far was the first 15 minutes of my planned talk, but it happened to be the whole hour, but I think it was not wasted. I think it was not wasted. But again, I'm ready, because my feeling is that this is one of the most exciting developments in mathematics in the last many years. The idea that such simple geometric objects carry such a lot of information is definitely a very, very important mathematical discovery. And this is a new discovery. People started using this in the mid-70s only. The first results are mid-70s. And now there's a huge, yes?
So just to make sure I understand, given one polynomial, you're going to find one polynomial.
Yes.
But you're going to be interested in the end in solving a set of n different equations.
Yes, but the polynomials I'm talking about should be generic. They should belong to a generic set. So I feel free to change my polynomials. I want them to preserve, my changes to preserve the polyhedrons, but otherwise the coefficients, I'm totally free to change coefficients.
So I thought I heard you say in answer to John's question that given one polynomial, the coefficients are always
generic. It is a small set. The set consisting of one polynomial, then it can never be a generic set.
And then I thought I heard you say that you want to choose the coefficients of each polynomial to be generic. generic.
If I have a system of polynomials and I am asking a question, how many solutions does the system have? I get the following answer. For a generic system with prescribed Newton polyhedra, the number of solutions is this. But for particular, the number of solutions can be much smaller or much bigger.
And, okay, maybe we should say this for next time. But
Yes.
or in private, but I still now don't understand. I thought I had understood what you meant by non-generic, but now I don't, because given one polynomial, you're telling me that every single polynomial is non-generic.
What you are given, not one polynomial. From this polynomial, you to take only its Newton polyhedron from this polynomial. And after that you say, okay, I don't care whether I'm dealing with this precise polynomial or with a generic polynomial with the same Newton polyhedron. So I start with the initial system of equations, which definitely involves very specific polynomials. I can say more or less nothing about the number of solutions. But what I can say, I do not believe that I really know all the coefficients precisely. Therefore, I say, okay, I allow myself to change the coefficients. Actually, you do not need to change them a lot. You need to change them a little bit, but arbitrarily, correct? And I'm asking, what will be the generic answer for polynomials from any generic set of polynomials satisfying these conditions?
The same as asking what is the maximum number?
Yes, and no, it is not the maximum, because maximum can be, for example, if all polyhedra are the same, you take the polynomials, the same polynomial repeated 25 times, and the number of solutions is going to be infinite. It is not the maximum number, but this number is true for any system with prescribed polyhedra, except of systems whose coefficients fall into a very thin subset of the possible set of coefficients. I think for physicists it must be a very natural thing to do. You never know exactly the numeric values of your polynomials or your functions, whatever. Therefore, you must allow for small deviations. And small deviations is the only thing you really need. What you think you know, that these coefficients have to be 0 and that's it. That means you know the polyhedron. Okay, thank you very much, but it seems we need to stop at this point.